Okay, so this is the second problem we're going to solve. A water tower is a spherical shell with diameter of 8 meter. The shell is supported by a single 30-meter long vertical cylinder with diameter is 2 meter. The wind with a uniform velocity of 20 km per hour which blows over the whole structure. That means the spherical shell and the vertical cylinder. We need to calculate the bending moment on the base of the tower due to this wind. The air is 20 degrees centigrade and the sea level, which says you may need to do some extrapolation if the graph is too large. So I believe you know what is extrapolations, and I discussed during the Tut session. So maybe I'm just skipping to keep the video length just as small as possible. So let's start with the solution now. So we'll say that this is actually the this is the spherical water shell with 8 meter diameter, and we said this is ds. This is actually the diameter. Okay, ds is for the sphere. We said sphere, and this is the 30-meter long cylinder. The diameter is 2 meter. So we said we just define this equal b 30 meter. Right, we know the wind velocity is 20 km per hour. So wind is blowing this way. So this is the direction. So we calculated the velocity. We converted the velocity from kilometer per hour to meter per second. So this is simple. You need to multiply 1000 here, and then it is 60. That means 1 hour. So 3600 second. If you simplify this, then you will get this velocity. Okay, that's easy. But now the thing is, we need to calculate the moment, and you know how to calculate the moment. So the moment is the force into the the distance, and simply this is the formula we know. If we want to calculate the bending moment here, we actually need to calculate the bending moment on the base of the tower, okay, due to the wind. So now what will be the formula for the bending moment? Yes, so if you agree me, the bending moment, this is actually the distance and the force. So what force will active? This is the question at first. So what sort of force we're going to consider? So this is the air is blowing this way. This is the spherical shell. This is the cylinder. So definitely the drag force is the acting force here, and the corresponding distance. So this is actually the base. This is the base. Okay. So we need the drag force and the corresponding distance, and you already know actually the moment. If we consider the moment, then we need to consider the distance from the center. So now the thing is, we'll get two different things. So the bending moment due to this spherical shell, and the bending moment due to this long the cylinder. So two things. When it is so that means we need to do some summation like of the bending moment of this and this. So you see here I wrote the formula. The moment m is the drag force of this sphere. We are going to calculate the moment due to this sphere. So the drag force is the acting force here into the distance. What should be the distance? The distance should be, this is the base. So distance, this is the center. So this distance. So it is d. So half this point this is the centroid. So it should be half of this ds. So let's say this is ds over 2, and plus this distance b, this length. So this is actually b. So this is will get the moment for the sphere. And now when it is the cylinder, then you see the drag of the cylinder. So it's a drag of the cylinder and the distance. So distance, this is the base, and it is the centroid maybe. So it should be into b over 2. So that's easy, right? in this question, you see it is in 20 degrees centigrade temperature, right? The air is 20 degrees centigrade temperature. So at 20 degree, we know the density is 1.2 and the viscosity, the dynamic viscosity is this. So that we got from the the table. So now we will start this with the solution. Okay, so according to the formula of the moment, we actually need the drag and for sphere and cylinder. So you already know the formula for the drag. So this is you're familiar with this formula. It is half the density, the velocity square frontal area, and the drag coefficient. So that means we need we know the density from here, we know the velocity, we can easily calculate the area, but what we need is we need the drag coefficient, right? So we need the drag coefficient for sphere and for cylinder to calculate the corresponding drag force of the sphere and the cylinder. So if you went through the slides that I sent to you, you can see we got a chart for the drag coefficients. You see here, this is actually the drag coefficient CD, the y-axis, and this is the Reynolds number. Look, the dotted line for a smooth cylinder, the solid line is for the smooth sphere. So we are dealing with definitely for the smooth problem. It's not rough surface. It's not mentioned here. So if we want to get the CD, we can use this chart, but we need to know the Reynolds number. If we know the Reynolds number, then we can calculate the corresponding CD from here. Yeah, so you can see some formula is given. Anyway, so what we need to do is we need to calculate the Reynolds number. That's the question. So now, if we go back to the solution, so what will be the Reynolds number? You see, the Reynolds number for S, that means the S pair. So you already know the formula. Reynolds number is the density, the velocity, diameter, and the dynamic viscosity. So we know density, we know velocity, we know the diameter, and we know everything. If we calculate it, we will get this is the Reynolds number for a sphere. For cylinder, we will get this. So now we're going to use these two values for a sphere and for cylinder, and then by using this table here, you can see this is for the smooth sphere, this is for the cylinder. So initially I believe for the sphere we had 2 point something into 10 to the power 6. So this is in log scale, so you see it is 10 to the power 6. So this is 2, 4, 6, 8, and this is 10 to the power 7. So we found it intersects the curve here, so we need to get this corresponding value. So maybe this is 0.2 something. So let's say we already calculated the drag coefficient. Yeah, so from the chart that we have, we got the CD for a sphere is 0.25 and CD for cylinder is 0.32. So that means once we know this drag coefficient, then it is easy for us to calculate the drag force and the drag for the sphere and the cylinder. So when it is a sphere, you see half rho v square s and the CD. So the frontal area is important. So in this case, you see it is pi by 4 d square. So this is the area, and we know the density, we know the velocity, and the other things. So this is the drag force for a sphere. And now we will calculate the drag force for cylinder. So for cylinder, I actually want to mention this. This is the same formula you can see. We said half rho v square s and CD of cylinder. So I actually want to highlight this section here, the frontal area. Where is cylinder actually? You see, we are taking this is the frontal area. Frontal area is actually the area where you can see from the front in simple mode. So this is actually the cylinder. So if you see from the front, you will see it is like this. Yeah, you will see it is like this. That means you will see it is a rectangle, and the area of the rectangle is the length and this height. So it is 2 meter. So the diameter, you will see it is a rectangle, like a rectangle. So it should be 30 into 2. So you see 2 into 30, and the other thing is just the simple thing. So you got 356, and now it's easy. You know B, you know diameter of this, you know diameter of this, and you know drag force. So calculate everything here, then you will get the moment. That's it. Right, so if we calculate the moment, we just put this formula, substitute all the values, and we got it. So that's it. So I believe this is not a big problem. But what I will suggest you actually, this is really important. So I'll tell you, okay, try to find out some problem, something like that for the final exam, and practice it.